Hello everyone! Today we take a closer look at the mechanical design of the Rui Mark1, including general layout, frame, motion system, components and much more. My name is Kevin and I'm the founder and lead engineer of Richner-Precision, a small Swiss company that builds all kinds of cool machines. And yes, sometimes I wear sweatpants to work. That's how you know you made it. Let me start by showing you an older machine of mine that I designed around 2023 and why it's so bad compared to the Rui. I really could not find the pictures anymore, so here I show you some old stories from our business Instagram and the 3D files in Fusion. I'll split it into 4 stupid design choices. First, form over function. Over the years I've designed and built around 20 different CNC machines, mainly routers, plasmas and mills, and I've grown to love simple design more and more. There's a famous saying, perfection is achieved not when there is nothing more to add, but when there is nothing left to take away. I think the Rui is close to fulfilling this premise. The Nexa Pro, however, was miles away. Then the initial idea was to have a design that used a lot of sheet metal parts for its stability, since we can get those manufactured locally in Switzerland or even fully in-house now. We recently acquired a large fiber laser, a deburring machine and a press brake to make that possible. I couldn't be happier. I mean, who doesn't dream of filling their workshop with big heavy machines? I also wanted the legs to be a structural part of the whole frame, which in hindsight was an absolute stupid idea, because you couldn't remove the legs for transport. That's why I made it exactly 795mm deep, so we could still fit the machine through normal doors, which made the wide travel very short, so it already starts with compromises. It's built around standard T-slot aluminium extrusions, which I'll express my hate for in one of the next points. It also uses different ball screw sizes on X and Y, because I didn't want the side cases to be too big, so I used 12mm for Y and 16mm for X. Now, to the annoying aligning problem. To align just one of the Y-axes, everything had to be first bolted together loosely and then aligned step by step with each connecting part. The aluminium frame had to be square while at the same time aligned to the sheet metal parts, which again hold aluminium extrusions on which linear rails are bolted using T-slot nuts. A ball screw is mounted to the linear blocks and has to be aligned with the bearing blocks, which are again bolted to the sheet metal parts. So a total clusterfuck to align and bolt together. There are also a lot of covers everywhere to make it look more industrial, but most of them serve no real purpose. They don't cover any motion hardware or anything functional. Again, a pure form over function decision. The X-axis used the belt to connect the ball screw to the motor because I thought it looked better, which of course made it less precise, more complicated to build and added another potential point of failure. I could go on with this list forever, but this video isn't titled Roast of My Old Machines, so I'll try to keep it short. Second, let's call it self-blocking design. Each assembly step seemed to block access to the previous one. A perfect example of how not to design for maintenance. This machine was an extreme example of self-blocking design. If I wanted to remove, let's say, the X-axis ball screw for replacement, there were so many components in the way. I'd have to remove the rear Z-axis enclosure, take off the side covers of the X gantry, remove all bolts from the bearing blocks, loosen the screws on the X servo to release the belt, then move the spindle fully to the left and pray to God I could somehow wiggle the ball screw out. That's self-blocking design, and this machine had a crazy amount of it. I swore I would never allow this kind of design in any new machine again, because it makes maintenance incredibly complicated. Third, T-slot nuts. A hate poem. I really don't like using T-slot extrusions and nuts for building machines. so I wrote a short poem to make that clear. O T-slot nut, you crooked pest, you twist when tightened, fail the test. You slide away when struck in place, and mock the maker to his face. The rails I mount refuse to square, no edge to guide, no truth to share. Each twist, each tap, a guessing game, you leave my patience scorched in flame. Your filthy grooves, your useless gaps, a paradise for swarf and scraps. You promised ease, modular dreams, yet nothing square, or so it seems. The Nexa Pro did, in fact, use what felt like hundreds of T-slot nuts. Practically every mechanical connection relied on them. Fitting the spoilboard was less a mechanical task and more a test of faith. Align every nut perfectly, offer a quiet prayer, and hope the bolt you're turning actually catches the nut you so carefully positioned. After a while, that sort of faith-based assembly really wears you down. I hope you see why I have chosen to never ever build another machine based on T-slot extrusions. We will take a look at the electronics of the Nexa Pro in the next video. Now, finally to the design of the Rui Mark1. It started as a personal challenge. Design the best CNC router with the least number of parts. The goal was simplicity. Every component should have a clear purpose. No unnecessary parts, and of course, no T-slot nuts anywhere. Now, if I want to build a single moving axis for a CNC router, what's the absolute minimum you need for, let's say, an X-axis gantry? You need a solid gantry beam to mount all the components onto. The logical choice here is a heavy custom aluminum extrusion, which compensates for the height difference of rails and ball screw and has CNC machined mounting surfaces and threaded holes for everything. Then come 2 thick HGR rails, not those flimsy MGN types, with 4 medium preload blocks, a precision C5 ball screw and 2 bearing blocks, 1 radial on the right and 1 axial radial with preloaded angular contact bearings on the left. I found these excellent HM12 blocks that combine motor mount and bearing block into a single cast iron piece. That makes it possible to mount a servo motor directly to the axis instead of to a side plate. So no complicated alignment needed. Add a coupler, a ball screw nut mount and the plate connecting the nut to the linear blocks. And that's it. About 15 parts and some bolts. Not a single nut of any kind except the one for the ball screw. The only decorative thing I added is a small sheet metal logo plate. It changes nothing mechanically but looks great. And that slot you see underneath? It's not a T-slot, thank God, it's actually a guide for a waterproof light strip. The Y-axis follows the same philosophy. Both axes are built from custom extrusion that avoid any self-blocking geometry and allow perfect alignment without shims or adapter plates. One of the main design challenges in CNC construction is the height difference between ball screws and linear rails. Usually, you need spacers or mismatched parts to fix that. Custom extrusions solve it cleanly by integrating different mounting heights in the extrusion design and the same in the 25mm thick oversized side plates, so everything lines up perfectly. Instead of bolting on sheet metal covers, so the rails don't get covered in dust and chips, I just integrated the cover in the extrusion design. Simple and straightforward. Now to the general layout. There's a reason why the long axis of the Rui runs in X and not in Y. A common sheet size in Europe for wood, plastic and aluminium is 1250 by 2500 mm. With the long axis in X, you can machine full sheets front to back without cutting them down. Just add a roller stand in front and in the back of the machine. It's also much easier to load and operate. You can place the machine with its back against the wall and the front remains open. If the axes were flipped, the gantry would block access. The only minor trade-off of a long gantry is a bit more flex, but testing and simulation showed that with our very thick-walled extrusions, it doesn't really affect precision in wood, plastics or aluminium machining. The base frame continues the same idea of minimalism. It consists of only 6 parts, always bolted together from 2 different sides for maximum rigidity. Every single hole is threaded, not a single T-slot nut anywhere. Every extrusion is CNC machined, so all mounting surfaces are perfectly square. The frame is strong enough to be used as a desktop machine even without its steel legs, which is also how it's shipped. Fully assembled, legs detached. The legs and front and back covers were inspired by my old Nexa Pro design, just wider and better proportioned for this machine. Since most of the structure is made from aluminium extrusions, it's worth explaining how they're made, with the help of my most trusted graphic design software, Word. A steel die is machined with the shape of the extrusion. As you can see here, a picture of the die of our X-axis extrusion. A heated aluminium billet is then pressed through the die at very high pressure, producing the raw extrusion. Now it's still very hot, so it's cooled, straightened and then heat treated for strength. After that, it's saw cut, slightly oversized, fully CNC machined, measured for tolerances and finally anodized with a beautiful matte black color. For motion components, I followed the same philosophy. No hidden ball screws like behind the gantry or under the table and no complex covers or unnecessary constructions. Each axis uses rails and the ball screw side by side, mounted directly to the extrusion. The 2 Y-axis and the X-axis use 16mm C5 ball screws, while C uses a 12mm C5 screw. All bearing blocks are C5 rated with angular contact bearings. The rails are 15mm HGR type with 4 medium preload blocks per axis. Most machines in this price range use cheap C7 ball screws, which are fine for window openers, not for precision routers. C5 screws were the only real choice. They may seem similar, but C5 ball screws are nearly 3 times more precise than C7 in lead deviation. But of course C7 is much cheaper and most customer doesn't know what it means anyway, so many manufacturers just get the cheaper option. We also use the same rails and blocks for all our machines, so it makes inventory a lot easier. The table is a hybrid design that combines aluminium extrusions with MDF inserts. This is the one place where T-slot extrusions actually make sense. 10 of them are mounted along the table and open for slotting in T-knot nuts from the front and back. It's perfect for quick mounting of all types of work holding, like clamps, vices, bolts, fixtures, or vacuum pads or tables. The MDF insert sits slightly higher and serve as a spoil board so you won't cut into the frame when going a bit too deep. Because all base extrusions share the same hole pattern on the front, you can easily mount vertical plates or fixtures for side machining, like the one we sell as an option. The C-axis is a very simple but sturdy design, based on an 18mm aluminium plate. It's easy to mount square, using just 4 screws and the locating edge on the back. By the way, this machine has lots of locating edges. They make assembly square and foolproof. You'll find them on the back of the C-axis, on the side plates for aligning the gantry, and again lower down on the same plate for aligning the blocks parallel to the axis. All linear rails have locating edges as well for perfect straight mounting. For Y, for X, and even for C. All locating edges are CNC machined on large VMCs, guaranteeing perfect accuracy, squareness, and straightness. I just really like this machine a lot. It has so many design decisions that make my life easier as a manufacturer. These are things customers will never notice, simply because they don't have to build the machine themselves. For example, the X-axis servo mounts directly to the extrusion, so the entire gantry, complete with wiring, can be assembled flat on a table and later dropped into place between the side plates. Makes it much easier to build like 10 of them at the same time. Next, the cable chain runs directly along the extrusions, requiring only one small sheet metal bracket on the rear of the Z-axis and nothing else. Simple. There are also accessories, like a full enclosure with door interlock switches and safety windows. I always try to make sheet metal parts symmetric, because it's cheaper to produce. Here I use the same door 4 times, and the side panel is also the same, left and right. Same, for example, for the legs. They are always the same, front left to back right and front right to back left. I also added a lot of holes, which makes it possible to attach accessories or a lower level for storing materials, or also whatever else you can think of. I also always try to make the machines open for mods, so the sky is the limit. There's also the ATC option, which I will talk about more in the next video on electronics. Or how about a water table for plasma cutting? Because in theory, the Dominator controller could support a daughter board for THC voltage sensing. Now, did I change anything after many hours of hands-on testing with the prototype? Yes, but only small things, like slightly adjusted hole sizes or a few millimeters more or less on the ball screws and rails. You know, details. I know it's very unlikely that small children will be near the machine, but just the thought of it makes me uneasy. That's why I added left and right Y-axis covers. A small, safety-focused detail, inspired by being a father of a young child. The RUI is built around one guiding principle: maximum performance with minimum parts. It's simple, rigid and thoughtfully engineered. Every feature exists for a reason, and every design choice reduces complexity without sacrificing precision. I think that's everything on the mechanical side. Please tell me if I forgot to talk about something. In the next video, we'll look at the electronics and controller development. I hope you enjoyed this video, and I'll see you in the next one. Tschüss and goodbye.